Hello everyone, this is Fei. I'm a research scientist at Google DeepMind, and I couldn't make it to CVPR due to visa reasons, but I still want to talk to you guys and share some thoughts on grounding language models for robot planning in 3D scenes. Over at Google DeepMind, we have been investigating using foundation models for robot planning and control. Some of the flagship projects including SeiCan, interactive language, coded policies in the monologue, and NLMap SeiCan. We have been investigating using foundation models for high-level robot planning, such as task planning, and we have also been thinking about low-level control, such as generating control signals so that you can navigate and manipulate, or generating code that can use the code as a policy to achieve long-horizon robotics tasks. Just to give a concrete example, here is SeiCan. In SeiCan, we propose to ground language in robotic affordances that we can then understand human instructions and then help human to achieve some tasks. In this particular example, the user input, I spill my Coke on the table, how would you throw it away and bring me something to help clean? And the robot is using a language model and affordance model to derive a plan. In this case, it says, find the Coke can, pick up the Coke can, go to the trash can, put down the Coke can, and then it still needs to find something to help clean, so it went to find the sponge and then bring it back to the user. So it is a very complicated task and requires language understanding and also understanding the surrounding environment as well as the robot's own capabilities. So here it put down the sponge and the user will use it to wipe the table. Here, we are using language model for robotics, but it doesn't just work out of the box. It requires some massage, so to speak, to make it work. So in this case, if you directly ask a language model, I spilled my drink, can you help? GPT-3 will say, you could try to find the vacuum cleaner. Lambda will say, do you want me to find a cleaner? And Flan will say, I'm sorry, I didn't mean to spill it. The problem is that language models are trained in a way that is not grounded in the environment, not grounded in the scene, or robots' own capabilities. Our robots can only do a fixed set of commands and need the problem to be broken down in actionable steps. This is not what the language model has seen. So we need to let the language model speak robot language and also understanding robots' own capabilities. So one way that we can bake this robot capability into language models is to use robotic affordances. So here is a video of the robotic affordances. You can essentially get it for free if you train a policy with reinforcement learning. They provide value functions, and value functions can be seen as a proxy for affordances. In the visualization in this video, as you can see, when the robot is in front of the bag of chips and water, the value function or affordances for picking up water bottle and pick up bag of chips is really high because that is what is possible there. So of course you can get the affordance from a policy. You could also get it from like scene understanding or structure scene understanding. Right, so then in the SeiCan work, we basically have two branches. One branch is the language model branch, where it will score your steps that are relevant to your final task. For example, if a task is how would you put an apple on the table, then anything that is related to apple get a high score. And the world grounding part is done by task affordances with value functions. Anything that the robot can do will get a high score. In this particular case, pick up an apple is not possible here, so find the apple would be the next step. And then the robot repeat this step until the entire task is finished. Okay, so this is basically how SeiCan work. It's also how using language model for robot planning works in general. So can we do this a little bit better? Can we do it in a more general way? Just imagine in this scenario, in SeiCan, we are only operating with 17 objects and around 60 action primitives, so scoring over them is feasible. However, when the robot is faced with a messy kitchen like this, it is impossible to enumerate all possible actions that the robot can do. So we propose a new way of doing this language grounding. We call it grounded decoding. So grounded decoding basically decode the plan token by token using a generative model instead of scoring all possible actions. So language model does this autoregressive decoding all the time. So basically every step you get the logits for all possible tokens and then choose the highest one or using beam search to find the next token. Now we also have an affordance model that is open vocabulary. What does that mean? It means you can score a partial string. When you score a partial string, you multiply the token language model score and affordance score, similar to how SEICAN works, and choose the highest one. So and then you repeat the step, not subtask by subtask, but token by token, and then you can derive a detailed plan to finish a task. We can also use the grounded decoding in a fairly innovative way. Basically, we can treat grounding as a sort of a tool. So here we use left bracket to means start grounded decoding, and we then use right bracket means finish grounded decoding. And whatever you see that is purple here triggers grounded decoding. So whenever the language model mentions something in bracket, it means it has to be something that it can see. So basically here it is multiply the score from a language model and the score from a detector. So this makes a plan grounded essentially by using a detector. So in this case, human want a soda that is not Coke and a fruit. So there are many soda that is not a Coke and there are many possible fruits, but the robot can only see a Pepsi and an apple. So it decodes, I will find a Pepsi and an apple and then bring it to you. So it generates grounded decoding. Similarly, it can also work for other cases. Just for the first example, I want to wipe some spill, and the robot say, I will bring the paper towel because that is what in the scene. Okay, so far we have shown that you can do the grounding based on your current observation, but we also want to do the grounding in your entire scene. You can explore the scene first and then get some representation, and then based on this representation, do decoding based on the language models. This representation is what we would call open vocabulary queryable scene representation. So first, the robot does exploration. It is explore the scene and store the environment. Second, it can do region proposal and VLM features, collect clip features, for example, and then do some sort of clustering, multi-view fusion. And this basically builds open vocabulary queryable scene representation. So you can query it with different names, such as the Coke can be queried with Coke, or it can be queried with red can. So then we can do the similar SEICAN procedure, but with this type of scene representation. The key difference here is that we, instead of using a fixed number of options, we would generate the object proposal and then query the scene representation to find the location of the objects. So it is more open-ended and can finish more tasks than SEICAN. Just to give you an intuitive example, let's go over a few runs of this, what we call open vocabulary scene representation, a SEICAN policy. We also call it NL map SEICAN. NL map means natural language map. So we can either run a scripted policy to do the exploration, or we can run frontier exploration for any novel environment. Then we end up with a scene representation that is represented in a clip point cloud. So basically we collect X, Y, Z location and clip features. And then you can query it with natural language, such as napkin box. And then you will get a heat map of where the napkin box would be. So it's also 3D, which is important because if it is too high, the robot cannot reach it. So you also contain some affordance information, so to speak. And let's see the robot finish one of the tasks. The task would be to put the multi-ground chips in the woven basket. So these two concepts are novel to the robot. However, because it has already explored in the scene, it can find where is the multigrain chips and where is the woven basket. And then it proceeds with picking up the multigrain chips and then place it in the woven basket. Cool. There are some more demos, but I don't think we'll have time to cover all of the demos. If you are interested in this work, feel free to visit our website. If you have any questions, feel free to email me or the other authors of these papers. Thank you so much.